Okay, so I'm going to go through this AP problem. It is question number 2 from the 2012 AP test, and I believe this was on both the AB and BC tests. So it says let region R be the region in the first quadrant bounded by the x-axis and the graphs of y equals ln of x and y equals 5 minus x, as shown in the figure above. And so this is the figure of these two graphs, and this is our region R as they just stated. So it says first to find the area of R. Well, we know that integrals can be very useful for this. Essentially, an integral, you're just taking different, you're taking an element and you're taking something like this, and it has a width dx, and it has a height, whatever f of x is, and then you're just summing all of those up over a certain interval, and so that's written like this over some interval of f of x dx, and that gives you the area. We do have two different functions here, and so what we're going to have to do is divide this into two different sections, because we can't, the function changes at this point here. And what's going to be critical to finding that point is just graphically graphing these equations and using the intersection function on your TI-84, which I just figured out how to have a cool emulator for on my computer. It behaves exactly like the TI-84 Plus Silver Edition. So we're going to graph both of these. Y equals ln of x and y equals 5 minus x. Graph. Okay, so it looks pretty much like it did in the video, and now we're looking for this intersection point right here. So we're going to go to Calc, and we're going to go to Intersect. First curve. Whoops, I didn't like that. Okay, there we go. Yeah, there was a discontinuity at x equals 0, so I didn't like that second curve there. Guess. Just bring yourself in close so that it doesn't take a long time for the calculator to do its thing. And the intersection, we'll call this intersection AB, and that intersection is 3.69344 and 1.30656. 1.30656. I need to find a way to get that thing to float on the top window so I don't have to keep doing that, but that's a later issue. And so we have these 2 points A and B, and in case you didn't know, on the AP test, as long as you define variables like A and B, it's perfectly acceptable to write this as your integral, so you don't have to write some obscene number up there. There's absolutely nothing wrong with doing that. And so in order to find the area of this thing, we're going to take the sum of the integrals from here to A, and then from A to 1, 2, 3, 4, 5. So we're going to go from 1 to A, and from A to 5 with those respective two different functions. And so writing that out, we're going to have the integral from 1 to A of ln of x dx, since that's this first curve here. And then our second curve, we're just going to add the two areas from A to 5 of 5 minus x dx. And that's something we can just really easily evaluate on our calculator here. I'm going to, let's see here, we should set a variable. So we're going to let 3.69344, and we're going to have that be set to x, or how about A? Yeah, we'll set it to A so it matches up. Okay, so now that's set to A. That's set to A, and so now we also have these already stored in here, and so we can do math integral from 1 to a of variables y_vars function y1, since that's our function that's stored as y1, dx plus math 9, and now we're going to go from a to 5 of y2 dx. And that area is 2.9858, and they have you round to 3 decimal places on the AP test, so 2.986. And it's called those in square units. And that is part A. Okay, so in the last video we went through and we found the area of this region R using some integration techniques, and we're just separated them into these 2 different sections that are bounded by these 2 different functions as well as the x-axis. This section for I'm going to do part B now, and this bit doesn't matter as much anymore, but we still are going to hold on to this this intersection point that we found, and that's going to be useful to us here as well. So part B says region R is the base of a solid. So this is kind of hard to picture. For the solid, each cross-section perpendicular to the x-axis, so cross-section perpendicular to the x-axis, well, I actually already drew one there, is a square. Right, but do not evaluate an expression involving 1 or more integrals, so we don't have to do just one, that give the volume of the solid. So we're trying to find the volume of some awkward solid that's bounded by this, and I'm going to try to draw this 3-dimensionally real quick. So we have like the y, the x, and the z here. So then, let's see, y, x, so then we already have like this, and then this is our base, and then the solid itself is going to be like, so we have all these cross sections, and all of these are squares. So if you turn all of these into squares, you get some kind of funny shaped thing that looks like this, and I guess that actually isn't that bad of a drawing. So that's what we're trying to do. And so essentially, in order to add all of these up, we're going to chop this bottom section into a bunch of infinitely thin rectangular prism things. And so if we have one of these rectangular prisms, it's going to look like this, because we know that it's a square. And so this base is going to be f of x, and then this height is also f of x since it's a square, and by f of x I just mean however far this is from the x-axis, and however far that is from the x-axis, that's also how high it's going to be. And then our width is just dx, since we're going perpendicular, and as you go across you can view these as tiny little infinitesimal changes in x, tiny little sections with widths dx. Well, the volume of this thing, the volume of this little one is f of x squared dx. And so what we can see is that that's the volume of this little one, but this thing itself is just a little tiny change in the volume. And so this thing itself is actually dv when we look at the big picture of things. So dv equals f of x squared dx. And then if we want to find the volume, all we have to do is integrate across this region. Now because of this intersection, because f of x changes, because f of x changes at this point here, we're going to have to split this up into two integrals just like we did in the last one. So let's do that. So our volume equals the integral from 1 to a, where a is just this point here, since that's the realm of our first function. F squared of x, that's just ln of x squared dx, plus the integral from a to 5 of 5 minus x squared dx. Don't try to square these out. Don't try to simplify things. This is literally all you need to get your full points on the AP test, because all it said was to write but do not evaluate an integral. And so no need to try and, use the binomial theorem to expand this out, because all you're doing is creating places for you to screw up arithmetic when you're supposed to be being tested on calculus. And that is how you do part B of this problem. So we've covered parts A and B of this problem, and now we're going to finally move on to part C. It says the horizontal line y equals k. Alright, so I'm going to draw some, well, after we finish reading, I'm going to draw some arbitrary horizontal line here. Divides R into two regions of equal area. Write, but do not solve an equation involving one or more integrals, so it's an integral equation, whose solution gives the value of k. So what we're looking for here is a way to find out, there's some line that divides this region in half here. And when you draw that line, y equals k, this area on the bottom here is the same as this area on the top here. And so we need to find out what that value of k is. We don't need to solve for it, but we just need to write an expression that has that as the only variable. So you could solve it if you wanted to. And this is a very interesting question. So what we're kind of looking for, keep in mind that you're not limited to integrating in the x direction. You can actually integrate in the y direction as well, as long as you have your equations in terms of x equals y instead of y equals x. And so that's going to be useful to us here. And so essentially what we're looking for is to have some region, or to have some line where if you integrate, if you take the area from y equals 0 to y equals k, then the area given by that integration there is equal to 1/2 the area of R. Well, it just so happens that we did find the area of R in one of the in the first segment. So really, all we need to do is put these two equations for the functions in terms of y instead of x. And then we can set up the integral, and then we'll be done. So what we're going to do is put these functions in terms of y. So we have y equals ln of x and y equals 5 minus x. Well, to solve this for x instead of y, we can just take both sides to the power of e. Well, take e to the both sides, and then you end up with e to the y equals x, since e to the ln of x is just x. And then for this one, it's pretty straightforward. Just add the x over and subtract the y over, and then you get you end up with x equals y. Sorry, x equals 5 minus y. Now, the length of some segment, so given a certain x, we can find this distance, since that's, x of y, and we can find this distance, at some given point. Well, in order to find the length of the segment we're trying to integrate through, what we want is, this is a little dy here. it's a change in y, we need, and this function is always going to be on top in the domain that we're in, and so we need to just say that it's going to be 5 minus y minus e to the y, because that's going to give us this distance here, and that's what we need to integrate through when we come this way. So that's kind of our new function. I'll call that g of x. G of x equals f minus y minus e to dy. And then, so we have that function that we've redefined, and so now all we have to do is do exactly this. So we're going to say that the area of this region from 0 to k, so the area from 0 to k, which is this area here, is going to be of g of x, sorry, g of y. So used to writing functions in terms of x. G of y, since we have y's. G of y dy, since we're looking at changes in y, is going to equal 1/2 this area of r. You could define that to be a of r, and then that would be perfectly acceptable as long as those match up there. And if you define g of y to be this, then that's perfectly acceptable as well. And so even though there are absolutely no numbers here besides this 1/2, this is an acceptable solution for part C. And I should probably write part C. All right, and that's it. That's how you go about tackling this entire problem. It's not an incredibly difficult problem, but you definitely do need to understand what's meant when you have changes in x, and and how that relates to the functions, and how you integrate in different directions, and how you set up different stopping points in order to give yourself more options when you're trying to evaluate areas and volumes of awkwardly shaped things. And that's it for this problem.